Hello everyone and welcome to Java Basics. Today we will learn about the Java Persistence API, which we acronym as JPA. We will learn about Spring Data and Hibernate. We will use all of that knowledge to change our Wordle clone application so it will save the data to the database in a way that is both easier, more powerful, and more efficient. The code for this video is available here. It is in the description too. Don't forget to start and follow me on GitHub while you're there, and here too while you're at it. Java Persistence API is an API that maps Java objects to an SQL database. As you might recall, an SQL database is typically a relational database, which means that JPA is an object relational mapping solution, an ORM. This is a common industry term, and there are many tools for ORM. JPA is the leading standard on Java, but there are others. JPA is a standard. That means the engineers that created Java decided how the API would look, but they didn't build the actual implementation of that API. There are, in fact, more than one implementation. The most popular one is Hibernate, which we will use today. Spring wraps JPA and adds another layer on top of it. Today, we will use Spring Data, which means some of our code will be specific to Spring, while other code would be pure JPA. You can tell the difference by looking at the import statement for the relevant classes. If a package is in the Spring hierarchy, it's part of Spring Data. If it's in the Javax, Java, or Jakarta packages, then it's part of JPA. This has all been a bit abstract. Let's explain a bit how an ORM works. On the right side, we can see a typical table with data in the database. We have an ID column. This is the primary key we discussed before. Then we have a couple of columns of data. In JPA, we would typically create a class with a similar name to the table and have fields matching the column names. JPA would typically map every row to an object instance. This is a gross oversimplification, as we do a lot more than that, but the basic idea isn't far off. Here we have a relational sample based on the code we will build today. The web user object includes a UUID that I shortened here to fit in the display. Notice I could use the UUID as the primary key ID column, but I don't do that here. Doing that would have implications on both security and performance, since the UUID might be generated in the client side. What I want to focus on in this table are two things. Notice the user ID column here. Notice that it's mostly a match to the ID column in the web user table. That is a foreign key, which we discussed before. This means we can find the games belonging to the user and the user who played the game. This is all very abstract. Let's get into the code. We start with the project we left the last time around. We create the web user class. I will use this to represent the user that comes in from the web. Notice I used the name web user and not user. There are two reasons for that. The first is to reduce ambiguity, but the second is that the word user is very common in programming. I don't want the name to clash. It's important to keep names unique in programming. We will add three annotations to the class. The getter and setter annotations are a part of Lombok, which we discussed before. JPA doesn't work with records yet. It needs classes that can be modified, so records can't be used. Unfortunately, to keep encapsulation, we want the fields to be private, and have get and set methods for every field. That is tedious. Lombok automates that tedious task for us by generating getters and setters for all the fields by default. The key annotation here is the entity annotation. This makes the class into a JPA entity, which will map it to an SQL table by default. An entity can be mapped in complex ways. I won't go into all the details. We can use things like the table annotation to indicate the table name and use other annotations to inject custom SQL commands. But we're not at that level yet. The first field we define is annotated with ID. That means it's the identifier for the entity or its primary key. Entities have a primary key associated with them, so we can find and differentiate them. In this case, the key is numeric and long. Numeric keys are typically faster. There's an interesting discussion about this, and that we should raise in the video on security, which I hope to make in the future. The generated value annotation indicates that we want JPA to set the value of the field. We did that before with SQL. It saves us a lot of hassle in determining the next appropriate value. Next, we add a field to store the UUID of the user from the web. It's just a string, nothing more. Next, we create a list of games. A game is a single round of Wordle that we played. We haven't defined that class yet. I'll get to it soon. But what we see here is a database relation definition. Every web user object will have 0 or many games associated with it. That makes it a one-to-many relationship. The mapped by attribute indicates that the web user ID should determine the mapping. We can even indicate the order of the games as they appear in the relation. There are many complexities related to relation mapping, such as eagerness, that I won't get into. But if you do proceed with this code, you should follow up on that. What we have here is a list of games that we can map to every user. There are 3 types of relations in JPA. The first and simplest one is one-to-one relation. Every instance of entity 1 will have an instance of entity 2 associated with it. This is rarely used in the real world. It looks somewhat like this in code. Notice the relation is a pointer directly to the other object. Any relation can be unidirectional, which means the relation points to one side, or bidirectional, which means the other side of the relation points back. In the case of one-to-one relation, both sides of the relation will just hold pointers to one another for a bidirectional relation. A one-to-many relation can point from one entity to multiple entities of the same type. This is the type of the relation we have there and is one of the most common relation types. One user plays multiple Wordle games. Each game belongs to only one user. We can still have multiple users, but each would have its own set of games, and each game would belong to one user. This too can be unidirectional or bidirectional. We already saw the code for a one-to-many side of the relation, but we didn't see the flip side. If the relation is bidirectional, the other side of the relation will have a many-to-one relation back to us, which is just a pointer back since there's only one parent. Notice that we can have a unidirectional relation with only the many-to-one side as well. The many-to-many relation is the hardest. It means multiple instances on both sides can be related. The way this works is through a table that maps the IDs of entity 1 to the related entity 2 IDs and vice versa. This means both sides of the relation have a list of values. A common example would be a blog post and its associated tags. A tag can be on many posts, and a post can have multiple tags. Since there are now 3 tables associated with a query, this is complex and expensive in terms of performance, so we should try to minimize this type of relation. We don't need to define the join table as we define it here, but when writing a real-world application, we probably should be aware of what's going on in the SQL that is generated for us. An entity requires a default constructor, a constructor that doesn't take any arguments, since the implementation of JPA needs to create an entity instance for us. It needs a constructor it can invoke. For convenience, I'll also add another one that accepts a UUID for the user I'm adding. Another convenience method we need to define is the addGame method. Since the game relation is bidirectional, we also set the value of this user to the game object. As you recall, this is a special keyword in Java representing the current object that we are currently in. If there's no list yet, we create the first entry. Otherwise, we add an entry to the existing list to include the new game object. We will use this method soon enough. But now we need to implement the game class. I will skip the class creation and go right to the code. In this new class, I can paste the annotation from the web user class, since this is also an entity. Here we also create a long primary key, but this time we define a different generation strategy. There are several ways to define a database-generated primary key in Java. The default generation type that we had in web user was auto. Auto uses a separate sequence table where identity uses an SQL auto increment column like we used in the SQL video. Each strategy has its advantages, and there are a few other strategies. The main reason I chose to use this here is so we can review the SQL differences when we run this later. This is the guess column, illustrating the current guess. By default, strings map to a 255-character database column. Here we specifically indicate that the guess has 5 characters. This can make the database smaller and more efficient. The column annotation lets us specify various things about the underlying database table. Columns such as its name, which might differ from the field name, and much more. Similarly, the current word also has 5 characters, and the attempt value is a regular integer. All of these map to the table columns. Finally, the inverse side of the bidirectional relation between the game and the user who played it is also within the game. Notice that here the relation is many to one and denotes the column used to join the table. Now that we created the 2 entities, we need to create repositories. As you recall, repositories store the data for the application. In this case, you will notice that instead of creating a class, I'm creating an interface. In this interface, we extend the JPA repository. This is part of Spring Data and not a standard part of JPA. Here we can define access to a JPA entity that will map directly to the SQL table based on the type of the primary key and the type of the entity. We write a method definition called findByUID. That returns the web user object. This is where Spring kicks in. The method we define in the repository follows a common naming convention. If we define a findBy method, it will understand the rest of the method name and will generate the right SQL query to satisfy the method name. In this case, JPA will generate this SQL statement to satisfy that method. We don't need to write the query. We will invoke that method and it will run the SQL, then provide us with a user object as a result. Notice that the result is an optional object. Optional is a Java class that lets us indicate that an object can be missing, a bit like null, but also more expressive than null. We will get to it in a little bit. We can similarly implement the game repository. I've skipped the creation code and went directly to the actual code again. It's only an interface. Here we can see a different type of method. When the method starts with count, it will generate a select count statement. In this case, notice that a number is returned instead of an object, since that's the expectation of a count call. Also notice we include two fields and separate them with an AND. One is for the word we're looking for, and the other for the specific user, which also happens to be a relation. This means we can count all the entries for the given user ID with the given word. This will let us set the value for attempts to a reasonable value. It will generate this SQL. The SQL looks a bit obtuse, but it is very similar to our previous code implementing count in the database class. Going to the Wordle service, we first need to make the class transactional. Otherwise, things won't work nicely. We then need to remove the previous database implementation. We now need to go to the place where we save the database and use the user and game repository instead. Let's start by deleting the old database code. We can easily find the existing user by invoking find by UUID. But as you recall, that method returns optional. That means that it might not find a result. It could have returned null, in which case we could have checked if null was returned, etc. The problem is we might have forgotten to check for null, and then we would have risked a null pointer exception. With optional, we are reminded to check. The or else get method will return the value of the optional if it is set. If the SQL query found a result, then JPA will create a user object and return it. But if it doesn't and the optional is empty, the following block will be invoked, and it will create a new user object with the given UUID. Either way, the web user variable will never be null. That's the important part. Now we can create a game instance and set both the word and the guess entry into it. We can then check if we have a user ID. If we don't have one, that is the first guess by a user. So the number of attempts is bound to be 0. We need to do that because we need the user object for the next query. And it will only work for a user with a proper ID. Since the ID is generated when the user is added to the database, this query won't work for a newly created user. We can use the count method to set the attempts value, and it will work exactly as it did before. We don't need to write the SQL at all. For the test code, I wanted a way to generate some statistics, similarly to the ones shown by Wordle. How many attempts it took to generate every word for a particular user. I could implement this method with a stream, but the code turned out really obtuse. Here we have a loop over the game object and a variable increment for every word value. Before we go into the test code that verifies this, we need to do a couple of things. We need to add 3 settings here. The first indicates that we want Hibernate, which is the JPA implementation that we're using to generate and update the tables for us. This is generally considered bad. In the real world, you would want to manage your own database tables, but this is a common shortcut when building an initial prototype. The second line indicates that we want Hibernate to print to the logs all the SQL queries it is running. This should be off by default, but for debugging, it is very useful. It provides insight into the things Hibernate does under the hood. Finally, we need to define the dialect of the database. SQL is standard, but databases aren't consistent with its implementation. We pick the H2 dialect. Without this, the code will fail in runtime. We need the last two for the test, application properties 2. So you should copy those 2 lines there. To start, we will create a new test class called test Wordle service and annotate it as Spring Boot test. The test is simplistic. We invoke the calculate result method and expect it to return the right result. We also make some assumptions related to get attempts per word. The test is also a bit broken since it expects the word will always be lymph. This is something we should fix later on, but let's run the test and see how we're doing. Naturally, it passes, but the interesting part isn't that it passes, it's the content of the console, which includes the run execution. The output here is the Spring Boot execution log. When something doesn't work, this is where you need to look first. Since we configured Hibernate to print out SQL, we can see it all right here. Scrolling down, we can see multiple calls to drop table if exists. That means Hibernate is removing old tables, since this is a test execution and it needs a clean environment before it starts running. Here we can see 3 calls for table creation. These include the tables we created for web user and game, but also a special sequence table, which Hibernate used to generate the ID for the web user class. Notice it makes no similar table for the game table. That's because that class uses a different ID strategy, for better or for worse. We can see below the insert into game call and the select from the user table and a lot of other SQL that we can map back to the code we wrote. This helps make sense of the code and understand what's going on. We wrote a lot of code in this video which might be counterintuitive. The reason is that we implemented a lot of functionality beyond the previous database sample. Overall, JPA spares us a lot of boilerplate and coding effort, but it doesn't save us from the need to understand what is happening with the SQL under the hood. If you have any questions, please see the comment section. Thank you.